the first lesson that we need to tackle. And of course, waves and optics. It's all about vibration waves. So before that, let's tackle first Hooke's law, right? Hooke's law. I'll show you an experiment here. Okay. Now, if I'm going to increase, this is the equilibrium position of the spring. Okay. So say applied force. So here the applied force is 0. If I'm going to increase the, okay, I will indicate the direction of the applied force. If I'm going to increase the applied force, this green line here indicates the displacement from equilibrium position. Let's go back. Okay. Right. So this is the equilibrium position of the spring, or the position where the spring is not yet disturbed. If I'm going to apply force to stretch the spring, right? The red line indicates the direction of the applied force to stretch the spring, and the green line indicates the distance moved or stretched by the applied force to the spring from the equilibrium position. So as I increase the applied force, there's also increase of the displacement from the uh, equilibrium position. Now, remember the third law of motion, Newton's third law of motion, action and reaction. There is action force and reaction force. So the action force here is the applied force, or the force that stretches the spring. And the reaction force will be the force reacted by the spring. This blue line pointing at that direction indicates the reaction force, or the force exerted by the spring. Okay, so here, these two quantities, the force of the spring and the displacement, are in opposite direction. Now, what if the applied force will compress the spring? Now, what will happen to the displacement? It goes to the direction of the applied force, and the restoring force will be in opposite direction to the applied force as the reaction force. Okay, the reaction force is the restoring force, or the force exerted by the spring, and the direction of the displacement from the equilibrium position is in the same direction to the applied force, but in opposite direction to the spring's force, or force of the spring. Okay, so that's what Hooke's law is. Hooke's law says that the force to compress or to stretch the spring is directly proportional to the displacement of the spring. Okay, let's go back to the PowerPoint. And it is represented by this equation where K is the spring constant, F of S is the restoring force or spring force, the reaction force of the spring, and then X here is the displacement from the equilibrium position. Let's use the standard unit of force, which is Newton. So again, K is the spring constant. What is this spring constant? Spring constant measures the stiffness of the spring. Okay, stiffness means how hard, how easy to compress or stretch the spring. Now, the large value of K, or the spring constant, indicates stiff spring. So it means the spring needs more force to compress and needs more force to stretch. While a small value of K, or small value of spring constant, indicates that the spring is soft. It means it needs a small force to compress or to stretch the spring. Okay, so X here is the displacement of the object from its equilibrium position, where X is equal to, if X is equal to 0, then it means it is at the equilibrium position. So I'll show you another uh, spring attached by mass. Okay, so if I'm going to attach 50 grams, I'll indicate the unstretched length and then resting position, right? So what happened here, there is increase of displacement from equilibrium position as I hang a mass of 50 grams. So if I'm going to increase the mass to stretch the spring, or I'll increase the weight hung to the spring to increase its displacement from equilibrium position, what happened as I increase the mass, there's also increase of displacement from the equilibrium position. Right. Now, let us compare the displacement of the spring as I increase the spring constant. Okay, again, observe. As I increase the spring constant, let me observe. Okay, I'll increase the spring constant, the same amount of mass hung, which is 250 grams. Right? So it means the greater the spring constant, the bigger the spring constant, the shorter the displacement at the same amount of force exerted to stretch the spring. So it's a shorter displacement from the equilibrium position. Okay, so what are the two forces acting on this mass M? Right? One is the force acted by the force of gravity, which is in downward direction. Right? There is force acting downward, which is the weight of this object, which is mg. Okay, and the reaction force, which is the force acted by the spring to the mass, which is in upward direction, which is equal to F1, which is equal to negative k x. Alright, so a negative here, negative k, indicates that the restoring force or the force exerted by the spring, I'll tell you later why is it called restoring force. The force exerted by the spring is also called restoring force. So the negative sign here indicates that the, the spring force is in opposite direction to the displacement of this object to the spring. Right? Now, the negative sign indicates that the spring force is always directed opposite to the displacement. So the force always acts towards the equilibrium position is what we call the restoring force. Okay? Why it always acts opposite to the. Now, if I'm going to stretch the spring and then release it, what happened? It oscillates. Why? So why is it called the restoring force? Now, let's have this simulation. A mass attached to the spring. Now, this thing here, this is the graph of force versus displacement, right? Now, if I'm going to stretch the spring, the displacement goes to positive direction. Now, if I'm going to compress this spring here, this spring, I'm going to compress the spring, okay, the displacement goes to negative direction. But if it is in equilibrium position, then no force is zero. Okay, the restoring force and the applied force is zero. Now, why is it called restoring force? As I exert force to stretch the spring, okay, okay, so there is force applied to the spring to stretch it, and that is what we call the applied force. Okay, the applied force goes to that direction, F away. And the restoring force or the force, reaction force of the spring, F of S. Restoring force, it means, the restoring force means the block or the force tends to return the block to its equilibrium position. Now, if the spring, now if this one is compressed, the spring is compressed, and the displacement is in negative direction, okay, then compress. The applied force goes that direction, okay, that is the direction of the applied force, right? The restoring force will push the block towards the equilibrium position, F bar. It restores the object to the equilibrium position. So that's why the force exerted by the spring is also called restoring force. Right? Now, when x is positive to the right, when you stretch the spring, okay, then since these two quantities, there's the spring force or the restoring force are in opposite direction, okay, when the position is at positive x, then the restoring force should be negative. And then when x is equal to 0, it means it is a system is at the equilibrium position. And if x position is negative, then the direction of the spring force will be at the positive direction. Right? Looking at this drawing, as you can see, as you can see, this is the equilibrium position of the system. It means no the resultant force is zero. Okay, so F of R or the spring force is zero, and as well as the applied force. Now, if I'm going to stretch the spring up to X position, the applied force will be in that direction. The restoring force will exert opposite to the applied force. This restoring force F of R tends to move the object M towards the equilibrium position. But when it is compressed, the spring is compressed up to negative x position, the restoring force F01 tends to return this object to the equilibrium position. F of R here is the restoring force. Now, what if it is in the vertical position, the spring is in vertical position, and it is hung by a mass M? So X of O, that is the equilibrium position of the spring, such a term. And then when it is hung by mass M, okay, Due to the weight of this block, the spring stretches from x of O, or the equilibrium position, to x. Okay? And then there is a reaction force of the spring. Since the weight is always in downward direction, then the restoring force or the spring force will be at in an upward direction. Now, if the force used to compress the spring, so the applied force will be at upward direction. Okay, it is compressing the spring. The restoring force will act opposite to it. That's F of R. And this F of R tells the object uh, to return its equilibrium position. Alright, so let's go back here. Now, if the object moves towards X, since these two quantities, F of R and X, F of R is the restoring force, are in opposite direction, the displacement is positive, and we have positive X, then F of R here is negative. The restoring force is negative, since these two are in opposite direction. Alright, and then if the system goes to negative direction, so again, these two quantities, the displacement and the restoring force, or the spring force, or force exerted by the spring, are in opposite direction, and the displacement goes to negative direction, then this one, the restoring force is positive. Right? And F of R here is 0. The resultant force here is 0. Okay? Since the object is at equilibrium. Sure. Alright? Alright. So if let's proceed to the motion of the spring mass system. Assume that the object is initially pulled to distance A, okay, from equilibrium position, okay, from rest, like this one, is pulled from equilibrium position to distance A, alright, and then release. What happened? It moves back and forth. And this kind of motion is what we call simple harmonic motion. The repeated motion is what we call simple harmonic motion. So when can we say that object is in simple harmonic motion? Before that, as the object moves towards the equilibrium position, F and A decrease, but V increases. Right? At x of O, F and A are 0. On the second Newton's second law of motion, these two quantities, the resultant force, F or applied force, and acceleration must be in the same direction. Right? Must be in the same direction. So, and these two are directly proportional. As an increase of F, there's increase of acceleration. As decrease of applied force, there is decrease of acceleration. Right? At x of O, at x equal to 0, it means equilibrium position, V is maximum when that object is oscillating. And the object's momentum causes it to overshoot the equilibrium position. Okay? The force and acceleration start to increase in the opposite direction and velocity decreases. The motion momentarily comes to a stop at x is equal to negative A. And also at A. It then accelerates back toward the equilibrium position. The motion continues indefinitely. Okay? When the motion continues indefinitely and it obeys Hooke's law, then that is what we call simple harmonic motion. Okay? Motion that occurs when the net force along the direction of motion obeys Hooke's law. The force is proportional to the displacement and always directed toward to the equilibrium position. So the motion of the spring mass system is an example of simple harmonic motion. This is an example of simple harmonic motion, a repeated motion. Okay? It moves up and down indefinitely. So that is what we call a simple harmonic motion. The spring system, this one is also in simple harmonic motion, right? Also this one, it is in simple harmonic motion. So these are the example of simple harmonic motion. But not all periodic motion over the same path can be considered as simple harmonic motion. So to be simple harmonic motion, the force needs to obey Hooke's law. Right? Okay. Now, if you're going to bring the block up to its maximum displacement, what we call amplitude, okay, the maximum displacement of the oscillating system, that is what we call amplitude. This one, A. That is the amplitude, the maximum displacement from equilibrium position. Okay, when you bring that up to amplitude or the maximum displacement, now the restoring force will be maximum. The restoring force exerted the maximum amount at this position. F of R is maximum at this direction. Now, from Newton's second law of motion, the force and acceleration are directly proportional and must have the same direction. All right. Now, if the restoring force is maximum at this position, so it means acceleration is also maximum at this position. So again, if we're going to stretch a spring and bring this block at the maximum displacement and release it, okay, the velocity of this block as this block approaches to the equilibrium position increases. V increases as it approaches to the equilibrium position. Why? Because the restoring force always acts towards the equilibrium position. So there is increase of velocity. All right. Then as it passes through the equilibrium position, okay, when that block is at the equilibrium position, then the velocity becomes maximum at that position. Now, since this is equilibrium position, the resultant force is zero. So F of R here is zero. If the restoring force is zero, then we can say that acceleration is also zero. So, since these two quantities are directly proportional to each other. Right. Now, once passes through the equilibrium position and goes to negative A, okay, negative A is the maximum displacement from equilibrium position, okay, when the spring is compressed, let's say up to negative A. The spring here is compressed. Okay, the spring is compressed. Then the restoring force will always acts towards the equilibrium position. So F of R goes to at that direction. Okay. Now at this position, F of R or the restoring force is maximum. Okay. It will act maximum amount of force at this position. Since F of R is maximum at the negative amplitude, then acceleration is also maximum. But what will happen to the velocity when it comes to negative amplitude? It will stop. Okay, it will stop at this position, negative amplitude. Then if that object stops, then velocity equals zero. And then since this block is oscillating, then it will return to equilibrium position. Okay, and then goes back to the amplitude. First at x and then to amplitude. Once that object attached to the spring or a mass attach the spring at the equilibrium position, and the amplitude, velocity here is also 0. Okay, and then again, the restoring force is maximum and the acceleration is maximum. All right. How about the velocity as it goes through negative amplitude? Now, as this block moves towards negative A, or the maximum displacement from equilibrium position, when the spring is stretched, as it moves towards A, velocity decreases. Velocity decreases. Right? Okay, so let us try answering a sample problem. It is all about Hooke's law and simple harmonic motion. So we have here a problem. A spring is pulled to 10 centimeter and held in place with a force of 15 Newton. So that's the amount of force that is exerted to stretch the spring up to 10 centimeter. Okay, from equilibrium position, that's the amount of force, 500 Newton. So it is asking for the spring constant of the spring, or the K value of K, the spring constant. Okay, so remember this. F of R, for the restoring force, okay, the applied force and the restoring force are equal. So if that is the restoring force, the applied force to stretch the spring, then that will be the restoring force. It's negative K X. All right. So we will look for the equation of the spring constant K. K equals F of R, or the restoring force, over the displacement X. Okay. So we have 500 Newton as the restoring force over the displacement X, which is 10 centimeter. So we will use the standard unit of length, which is meter. So we need to convert 10 centimeter into meter. And 10 centimeter is 0.10 meters. So I'll put it here, 0.10 meters. All right. So what is 500 over 0.10? Then put K here, negative. Right. So what is restoring force at the positive displacement? Huh? At this displacement, it's negative. So we have negative of negative becomes positive. Right? So we have 500 Newton over 0.10 meters. Then the spring constant is, what's 500 over 0.10 meters? That is 5,000 Newton per meter. Okay? Newton per meter. We have a positive displacement, 10 centimeter, since we stretch the spring. And then F of R at the positive displacement is negative. So we have negative by negative, so it becomes positive. We have 500 Newton. And 500 Newton over 0.10, we have 5,000 Newton meter. Okay? So this is the standard unit of the spring constant, Newton meter. So this is what I told you. Amplitude. Amplitude is the maximum position of the object relative to the equilibrium position. And in the absence of friction, an object in simple harmonic motion will oscillate between the positions positive and negative 8. So we have shears. Example, assuming that this horizontal plane is frictionless, this is negative amplitude, which is the maximum compression of the spring, negative amplitude. And then position between the equilibrium position and the negative amplitude is negative x. And then we have the maximum displacement when we stretch the spring, we have positive amplitude. And the position between them, the equilibrium position and the amplitude, we have position x. Okay? So with the absence of friction, if we're going to stretch the spring up to its maximum displacement, which is the amplitude, okay, it will oscillate from A back to negative A, and then we'll go back to A. All right. So if friction is neglected, and then we have period and frequency. Period in symbol big letter T. So this is the amount of time that it takes the object to complete one cycle. You can still remember the uniform circular motion. When that object moves around the circle, okay, the time required to move around the circle is what we call period. And if you move around the circle completely, and that is one cycle. So what is one cycle in a simple harmonic motion? One cycle will start, if you're going to stretch the spring or bring the mass from A and then release it, when the mass moves from A, then back to negative A, and then back to A, that is one cycle. So again, one cycle is from A, positive amplitude, then goes back to negative A, and then goes back to A. That's one cycle. And the amount of time it takes to move from A to negative A, then goes back to A, that is what we call period. Since that is time, then we have a standard unit of time is second. All right. And then the frequency. The frequency in symbol F is the number of complete cycles of vibration per unit time. So meaning how many times it can move from A to negative A, then back to A in 1 second. Right? That is frequency. So if this block moves from A, then goes back to negative A, then go back to A in 5 times in 1 second, then the frequency is 5 cycles per second. So if the block moves from A to negative A, then goes back to A in, let's say, 10 times in 1 second, then the frequency is 10 cycles per second. And one cycle per second, 1 cycle per second is 1 hertz. That is named after Henry Hertz. So if the frequency, if moves 10 cycles per second, the frequency is 10 hertz. All right, and frequency F is reciprocal to the period. So F is 1 over period. Okay, so again, 1 cycle means a distance from A to negative A, then goes back to A. That's 1 cycle. And the time it takes to move 1 cycle is what we call period. So for example, if this block moves from A, then towards negative A, then goes back to A in 7 seconds, then the period is 7 seconds. Right? So what's the cycle? What's the frequency? That's 1 over 7, since frequency is reciprocal to the period. Okay, so Newton's second law will relate force and acceleration. So the force is given by Hooke's law, So these two forces, if it is equilibrium, it means two forces are equal in magnitude but acting in opposite direction. The applied force when you stretch the spring will be in opposite direction to the restoring force or the force exerted by the spring. Opposite direction but equal in magnitude. So meaning the restoring force Fr is equal to the applied force F of A. Alright, that's F of A. Fr is represented by an equation negative Kx, where K is the spring constant and X is the displacement from equilibrium position. And M is the mass attached to the spring. And A is the acceleration. Okay? So remember Newton's second law of motion, F equals ma, mass times the acceleration of the system. We have mass times the acceleration of the system, or A, mass times the acceleration equals negative ax. So we have the equation of the acceleration, negative k over m times x displacement. So as you can see, what is constant here? The spring constant and the mass. As the system moves, oscillates, there's no change of mass attached to the spring, as well as the spring constant. So it's not changing. So this is constant, negative k, negative spring constant over m. Okay, but what is changing? X, the position x. So when there is change of position, it means there's also change of acceleration. So acceleration varies, depends on what position is this block located. All right. So that is the acceleration of an object in simple harmonic motion.